Hi, my name is Alexander Rudenko. I'm a lead gameplay animator, and today I want to talk about physics in animation. My journey began at Banzai Games, the very company that developed Cascadeur software for animation. I worked there for 2.5 years, and since then, I have grown to love physical animation very much. If you check out my works, you'll see that almost all of them lean towards realism. They are exaggerated at times, but look believable enough. So, when you watch them, you believe that this character could indeed move that way. And all thanks to the understanding of the physics of motion. When I joined Banzai Games, it was initially very challenging for me at first, because their standard for animations was very high. It was impossible to achieve it right after school. It was like an invisible wall you kept bumping into, not quite understanding why you couldn't move forward. I still remember my first animation. There was a project with 3 factions: strong, agile, and precise. The strong one was all about physical strength, the agile guys were more of acrobats, and the precise ones were assassin-like. So I had to do a jump for the precise. I worked on this single jump for around a month. I was very surprised they didn't fire me. I am still very grateful to my mentor, who didn't give up on me. Thanks, Alexei. If you look at my first demo reel, that I used to apply to the studio, you'll see right away that the level is a bit low for a studio that is strongly focused on physicality. So, when I got more or less used to their software, Cascadeur, and my understanding of animation improved, I started to practice in my free time using references I could find online and create some personal works. Here's a quick example. Basically, it was rotoscoping, where I just copied the movement and calibrated my eye. In this regard, Cascadeur helped me a lot. There was a slightly different approach to the rig and interpolation. There was also a cool feature that allowed me to track the center of mass, which was set up for each character. In the end, I made some animations that greatly advanced me in my understanding of the body mechanics and physicality in general. This, by the way, is the answer to the question, how to become better as an animator. The answer is simple: you need to animate more. Well, ideally also with feedback from a more experienced animator, so that they can point out and explain the problem areas in your animations. Today I can highlight several key components of a good animation. In my opinion, these are the center of mass, rotation speed, inertia of body parts, and arcs. Let's break down each element. Starting with the center of mass. The center of mass is an abstract point that shows the distribution of mass within the body. In simple terms, it's the body's midpoint. This point provides us with the information on how speed is dampened, how velocity is gained, how a character falls or stands stably, and whether an object rotates correctly or not. The concept of the center of mass is quite extensive, but I'll try to briefly outline its key aspects using examples. We have a character with a center of mass set up. How do we set up a center of mass? It's actually very easy. You simply insert locators into the character's body, into joints. You insert them into the middle part of each foot, then into the middle of the shins, into the middle of the thighs, and into the controls of the pelvis and the chest control. Then, we continue with the head, shoulders, forearms, wrists, and the same on the other side. All of this is created inside the joints. Then, we create another separate locator, which will be our center of mass. Now we constrain this locator to all the locators we created with point constrain. Then we have to set certain values for this locator. I set these values roughly. Here, I put the weight of the body parts. I used some image, took the values from there, and rounded them to avoid figures like 0.9. This way, they would be more evenly distributed, and looking at the result, I can see that it works quite correctly. I decided to work with that. I didn't try to achieve very high accuracy because it's not important for our demonstration. Also, the mocap itself introduces minor errors. My main goal is to show you visually how it works. I don't need to make absolutely accurate center of mass. So now we have the center of mass ready, and we made sure that it works. Here I also made a vertical line, a simple cylinder, which shows where the center of mass is on the ground. And on the ground, I created a small plane that would be always located between the legs to see how the center of mass is positioned in relation to our support points. Support points are essentially our legs, or more precisely, our feet. I thought I'd show you how to make such a plane that follows the feet as well. You can see I move the foot, and the plane follows. Actually, it's just skin to a few bones. Let me show it. What you do is you create a joint inside. Create several joints like this. Create a plane. Your plane will have your dimensions. I set mine to 6. I kept a low number of polygons because it's not really important. And here I specify 3, 3. That's it. I've created a template. Now all I need to do is select these joints. Select the plane. Go to Skin. And here I choose Selected Joint and press Apply. Now the plane follows the joints. It just somehow skinned itself, and it's good enough for us. Right, so here I have 2 moving cubes, and I want this plane to follow them. I create locators in the cubes. Move these locators here. Move those locators there, to the edge of the foot as I had it. I can even shift it a bit to the side. And all I need to do is just constrain my locators, since I created them inside the cube. These locators. And all I need to do is constrain them with a point using only these 2 check marks, not all. And without keeping the offset. I simply press Constrain. That's it. Now, my platform, or rather my plane, will move along with the foot. If I don't lift it, nothing will happen. But if I move it in different directions, it will follow my foot and show the area located between my support points. Our center of mass can help us understand how balanced a pose is. As long as it remains within the area between the support points, the character is in balance and won't fall. But as soon as the center of mass moves out of this area, we start to fall. If we don't support it with a support point, we'll fall. Here I'm warming up, stretching a bit. Then I start swaying left and right. And as you can see when I sway, the center of mass doesn't move beyond the support point. Here I almost fell. Here I'm also close to falling. And now, as you see, the center of mass moves beyond the support point. When it was between the support points, it still somehow worked. But as soon as it moves beyond the support point, that's it. I start falling. So, what am I doing here? I try to put my foot down to catch my weight. Otherwise, I'd fall. There will be another example now, where I'll fall. See, if I don't put a support point, I just fall. Understanding how balanced a pose is under normal conditions is very easy. If, for instance, I stand in a certain pose, I can align the support points into a single line and see how balanced the character is. I have a special pose prepared here. This pose is quite dynamic, but the question is, how balanced is it? If we look from this angle, everything seems fine. But when we switch, for example here, something looks off. We see that our center of mass has moved out of the balance zone, where the center of mass normally is, when we're not falling. The character is visibly shifted in this direction. This indicates that she will most likely fall. To solve this problem, we simply shift her backward so that the center of mass is between the support points. Different ways to easily do this. Another easy way to do this is to simply take a vertical line approximately from the support point. We deliberately align them, draw a vertical line upwards, and look at the approximate distribution of mass. If we see that the shape on the left looks similar to the shape on the right, then we say that the pose is balanced. There's a feeling that the character still falls back slightly, but if we adjust it like this, then the balance will even out. Again, I talk about the volume of these 2 parts on the both sides of our vertical line. If we see that the volume on both sides is similar, we can say that the pose is balanced. But in fact, all this can be considered a balanced pose while it's within the limit of our plane. So, the closer we are to the edge, the harder it will be for us to stand, the more likely we are to fall. And for example, when we stand up, we also throw our center of mass. Look at how I push off. What am I doing? I push off with my hands, giving speed to the center of mass. The center of mass is thrown onto the support point and continues further. And then I just move it and place it in a comfortable position for me. Again, what happened? I fell, pushed off myself with my hands. The center of mass accelerated and crossed into the zone between the support points. I caught the balance here, meaning you can see that my center of mass was going one way, then I caught it, moved it back, and stood up in my usual pose. In fact, balance can also be seen in other situations, for example, like tightrope walking. Here you can see that many guys walk without safety harnesses. Apparently, They got an A in physics at school since they are so confident. Well, let's probably look at another example of how we can maintain balance. We can not only stand on two legs, we can also stand on one leg. And when we stand on one leg, our balance, or rather our center of mass, must also be kept above the support point. Since we only have one support point, the plane I made won't work for us anymore. So, we have to keep our center of mass over one support point. You can see that the center of mass moves slightly, which means the center of mass is never in a static position. Throughout this movement, I try to catch the balance. I keep the center of mass within the range of my foot. The last example on the topic of the center of mass balance. This is me trying to do a handstand. I was trying to stand on my hands. But I couldn't do it properly because I have almost no experience in this. And as you can see, I constantly move my hands, but I can't stabilize my balance and stand still. I always end up just moving my hands. You've probably seen the same thing in little children learning to walk. Initially, it's very difficult for them to stand, and they constantly try to balance. They are constantly trying to catch their balance, meaning trying to stabilize the center of mass. But it's very difficult at the beginning, and after a certain number of repetitions, they eventually acquire the skill of balancing on their feet. Everything in animation is like in life. The more attempts you make, the better you get. Alright, let's move on. We've covered a subtopic of the center of mass balance, and the next subtopic of the center of mass is the rotation of the character. If we look at my animations, there are actually a lot of rotations there. And this honesty and credibility of these rotations are achieved by the fact that they occur around the center of mass. It's a key point that all objects rotate around their center of mass. For example, we can consider such rotations in figure skating. Look, this girl is rotating around her center of mass. We can easily pause the video at any time, draw a vertical line, and we'll see that her center of mass is right here. Maybe a bit to the right. Somewhere around here, probably. If we try again to outline the shapes we have here and here, we'll see that they're roughly the same. In terms of volume, this indicates that the character is at the center of mass, meaning the character is in balance. If we look at my first demo reel, you can see I had issues with the center of mass. Here I have some acrobatics animation. I always liked it, but initially, undoubtedly, doing it without the understanding of physical basis was very difficult. For example, looking at this rotation here, you can see that the character is rotating around the pelvis, not around his center of mass. Because his arms are heavily offset, they are massive but they rotate around the pelvis. And this doesn't work correctly. So it's very important to pay attention to these things and understand how they work. The rotation around the pelvis, as you've just seen, is the most common mistake that many beginner animators make when working with rotations. It's understandable why it's done this way, because it's the easiest way. But we don't always rotate around the root control, but around the center of mass. It's important to remember this. Fixing such things is very simple. In school, I recommend to beginner animators, for whom creating a center of mass is like a 20-minute adventure, to create a locator and place it roughly in the character's center of mass. If, for example, we take this character, I simply create a locator and move it to the approximate center of mass. Right here. Now I rebake animation on the new locator, and just zero out all the translates. Now the character rotates around their center of mass. It's quite simple. For example, look at this guy who jumps off the bar and then lands here. We'll see that his pelvis moves nicely along a ballistic curve. But what we need is his center of mass moving along the ballistic curve, not his pelvis. So we move somewhere here, we create a locator roughly in the center of mass. It doesn't matter that it may move incorrectly somewhere in the beginning or in the end. Our task is to fix this most difficult part with the rotation. If we look at the center of mass now, we'll see that it doesn't really work well. What do we know? We know that during the flight, the speed is linear. So, for example, from here to here, I'll delete all the keys. I'll make the speed in space linear. I won't go into detail why it's linear because it'll take too long. Now let's work on the flight itself. I look for a part that I'm satisfied with. Like, this frame is good already. We delete all these keys here. Starting from this key we can delete. Let's see. Deleted. Now we refine the ballistic curve. As you can see, this is fixed very easily. Not everything works well, like it doesn't rotate much here, but rotates a lot here. But that's another matter. In general, fixing such things is super easy if you know what a center of mass is, and remember that character rotates around it. Now let's discuss the next point in our section about the center of mass. This is acceleration and deceleration. When moving a character, we usually see how their center of mass changes position. If we look at this example, we can immediately see how the center of mass works. It's important to track this center and understand how it should move. But in general, the rule is very simple. The center of mass cannot just accelerate on its own, nor can it simply decelerate. In order to accelerate, support points are necessary. For example, when we stand on two legs, we accelerate to the right and to the left, as we can give speed to the center of mass. And it's the back leg, like a spring, that propels us forward. It's during its contact with the ground that we gain speed. As you can see, I'm squatting a little. This back leg turns into a spring that I simply release and start running. Here for me, it's super easy. But if you consider the scenario where I try to start on one leg, it becomes much more difficult. It's not possible to accelerate reactively like that. You have to transition your character into a fall, which means we shift the center of mass forward, and once we do it, we start falling. Actually, any step is a fall. We always catch ourselves on a leg. And running is also a fall. As you can see, it's not possible to accelerate reactively like that. Although, I tried here. I managed to squat. I started the fall, but I couldn't push off properly since I was lacking the point of support behind me which should have propelled me forward. Right here, I position my leg on the opposite side, jump on this leg, compress it, and by releasing the leg, I gain speed. This works like a spring. Another important point is how we can decelerate the center of mass. For this, we need a so-called stopper, pressing with the leg according to the direction of the center of mass movement. This means that if you don't extend your leg forward, you simply won't be able to stop. That's exactly what's happening here. I'm running, trying to put my foot forward, but since I'm stepping before the center of mass and not according to its movement, I simply stumble and fall. It's impossible to stop like this. I tried a few times, and every time I fell, I just can't stop. I tried to extend my right leg forward, but I didn't tense it, so I just stopped moving my legs and fell. Thus, if you want to stop, you need to extend your legs forward and lean your body back a little. Now let's see how it works. I gradually start bringing my legs forward, and since I'm not tensing them too much, I have to take a few steps. I lean backward, and I slow down the speed of my center of mass. The same here. Gradually, by moving my feet, I slow down, and the last option is when we really extend our leg and tense it. And in this case, we stop sharply without any problems. And here, at the last moment, I extended my leg much further and squatted very strongly again. The analogy is the same as in the beginning of movement we discussed before. I squatted in order to start, and here I squat to slow down, to press my center of mass a bit closer to the support point. Alright, we've finished a large section on the center of mass, and now we're moving on to the rotation speed. This one is simpler to understand. If we're talking about physical animation or pseudo-physical animation, then rotation in a static pose in flight remains constant, unchanged as we saw in this example. So, essentially, this is how we rotate. If we consider real conditions, there is still air resistance, and it slightly slows down our speed. But to make things easier, this aspect is always omitted, and it's assumed that rotation is not affected by air resistance. If we consider rotation on the ground, then the friction force will come into play, and because of it, we will slow down. Let's first consider figure skaters. We've all seen their performances, but let me show you a video. Sometimes they reach incredible speed when spinning. Why does this happen? The answer is fairly simple. The closer we compress to our axis of rotation, the faster we spin. The further away our hands and legs are from the axis of rotation, the slower we spin. The axis of rotation as you might have guessed, passes through our center of mass. If, for instance, we divide the character, as I've drawn before, then approximately the left part should be equal to the right part. The leg makes this circle. So, the leg doesn't stay in one place. It's actually trying to compensate for this slight displacement. We can see here one part is slightly bigger than the other. That's why the leg draws this circle. It's like it's not rotating on the toe. Like a ballerina. If you look, ballerinas rotate, and their toe stays in one place. It doesn't move. But if we look at figure skaters, there's always a small circle drawn by their foot. I tried to simulate this rotation and attempted to record something similar. I couldn't spin for very long, but I think, for the sake of example, for clarity, we can use this one. When I spread my arms in different directions, I spin slower. When I compress, I noticeably speed up. This can also be seen in the graphs. You can see slower rotation here, and the acceleration happening here. Just when I bring my arms close to me, I accelerate. It's the same here. A more gradual speed. And here it's faster. Also, here it's visible why I couldn't spin for long. I couldn't keep the center of mass above the support point. My leg slipped somewhere to the side, and I started falling. And every time, if you notice, the same thing happens here. My center of mass starts wandering, starts moving to the side. Or my leg starts moving to the side. And in the end, I can't catch my balance. If I could stabilize my center of mass above the support point, then I could spin much longer. This takes us back to the handstanding or kids learning to walk. Practice, practice, practice is what's needed. If you practice, then you'll be able to stabilize this. And I'll show you more rotation in the air, changes in speed, and the rotation depending on the pose the character takes. All of this is quite conditional. Generally, nobody will ever demand this level of accuracy in games, such precise angular speeds from you. Your task is simply to understand how it works and nothing more. Here it's visible that the character rotates around their center of mass. But if we look at how the center of mass behaves, more precisely its projection, we see that it moves back and forth. This too, again, can be easily corrected. What do? We just take a snapshot of our center of mass. Basically, we take the information from it that we'll use to fix the center of mass. We see that the center of mass wanders quite a bit. Then we simply take all our translates. Here we only have the pelvis, knees, and feet among the translates. We take these 5 controls and bake them inside this locator. This across button basically does it through the locators. And after that, we simply delete the translation. Same as before. There. Our character with a perfectly stabilized center of mass rotates physically correctly. The center of mass doesn't wander anymore. Here it's visible that in reality, I didn't quite correctly make the center of mass. Here, when it rotates, I see the larger part appearing in turns on the left and on the right. But this is exactly because when I made the center of mass, I made it very roughly, and I set all the coefficients almost randomly, without properly knowing the exact weight of each part of the body. So, to sum up, it's important to remember that the rotation, namely the speed of rotation, strongly depends on the pose we take. If the pose is sufficiently distant from the center of mass, meaning our arms and legs are quite spread out, then we'll rotate slowly. As soon as we group and turn into, let's say, a ball, then we'll rotate faster. Let's now consider the next topic, the inertia of body parts. I also call this through motion. This theme is probably the most challenging for beginner animators. While the previous 2 blocks are more or less understandable, understanding inertia takes much more time. But let's break it down with examples, and you'll see that it's actually quite simple. I'll start with a somewhat funny example I recently saw on the internet. It's about the behavior of our face muscles during a fall. Here we see the inertia I'm talking about, the through motion. What exactly is happening? When falling, our bones stop. But the muscles continue moving because they had the same speed. Each part of the body has a certain speed. And when the skeleton stops, the muscles continue moving downwards, the hair continues moving downwards. It's important to understand that no object will just abruptly stop. It will try to continue its movement. If it's not just a skeleton, but a skeleton covered with muscles, then these muscles will definitely try to continue their movement. The same goes for clothing. If you look at this collar, the boy stopped moving, but everything else continued moving downwards. Let's look at another example I prepared. It's a jump with arms stretched out. Here, we have a similar case. I'm just trying to jump down and let my arms move further. I tense the arms just a little, not holding them in one pose too tightly, then let them fall a bit, and then I try to bring them back. It works like this. What does it show us? It shows us that the character, the head and the arms try to continue the movement after the jump. There was a certain falling speed, and the head and the arms keep moving. They continue their movement with this speed. The point is that here, the arm continues its movement. If we look at its spacing, we'll see that the arm doesn't stick in this point. I also have another example here. Almost the same jump, but here I deliberately let it freeze a little during the fall. And we immediately see that something's not right. There's some unnatural movement. We feel that something's off here. In reality, beginners often do this. They soften the moment of contact. Here the character freezes for a while, and then continues the movement. You should never do that. It's very easy to check it in the graph editor. You'll see that it's slowing down here. This slowing down is unnecessary, because when we look here, everything seems natural, there are no problems. But when we look at this version, we see that something's not right. The arms look stuck, they stopped at one point, and the head doesn't go down at all, only here, and the pelvis got stuck here. So, it's very important to keep in mind this through motion. Just like in this video, where the guys jumped and their muscles continued their downward movement. Why does this wave-like movement happen here? Because the muscles went down during the fall, stretched as much as they could, and they tried to go back, like a rubber band. When you stretch a rubber band, it also returns back. The muscles move up, then down, then up again. This is the body settling. And as we see, in the end, it settled down. There's some harmonic damping happening. The same thing happens with the fall on the back. When we fall on our back, all the points simply try to continue the movement. The arms try to continue the speed with which they were moving. And the head, when it goes down, we see how it works. It also achieves this through motion, as I call it. I made another version including common mistakes. Sometimes things like this happen. First, the character landed softly here, as if on a magnetic cushion. There's no stiffness here. And for some reason, it started slowing down along the TY. Along the TY, our objects shouldn't slow down. Here we see how it's lying down, very, very softly, and it looks unnatural. Let's look at this example. The hand here, for some reason, stopped in mid-air. It didn't continue its through motion. Then the head did something strange there too. I often see this, that the character stopped like this, and then the animator remembers that some bounces need to be added, and they do it like this. Of course, this is neither a physical nor a correct thing to do. Because each object has its mass, an object cannot just flick like this, making the same movements with the same amplitude in a short period of time. The same goes for this arm. Instead of following this arc, this through motion, it just goes in another direction and does something strange there. In theory, this shouldn't happen. Again, if we look at the original example. Here the arms started moving along the arc and kept following it without changing the arc. It's important to understand this. When the character falls in a relaxed way, they simply go down with this through movement. I call it through motion for a reason. It goes on by inertia. If an object started moving in a certain direction, its inertia will support its movement into that direction. A human doesn't have too many inertia points, so you don't have to worry too much about them. However, there can be more inertial points in the characters with various items like backpacks, guns, swords, and so on. In those cases, yes, there are points that need to be tracked, that need to be thought of as inertial, but again, once you understand the basics of how it works, it won't be a problem for you. This inertia is the very thing that gives life to a character. It indicates that they're real, alive. This again is the topic of physicality. In my mind, a character always consists of several key points. That's what I realized during my time at Banzai. I started looking at characters differently. If you haven't seen the video, Everything is a Bouncing Ball, I strongly recommend watching it. There's a shot from a cartoon showing you that everything is actually just bouncing balls. We see that the feet, pelvis, hands, shoulders, head, they're all essentially bouncing balls. And in my mind, when I think about animation, I actually see exactly the same thing, which makes animation very easy for me. I always see the character in a similar way. If go through everything we've seen before, let's scale it down to make it a bit smaller. This is the top of the head. I don't track the head itself, I track its top. So eventually, the character looks like this to me. If you've seen motion capture sessions and seen the raw data, you'd know that a character looks almost the same, just with more points. This is how I see the characters. And I always keep track of them, of these inertia points. That's why animating is very easy for me. I understand how it works. I understand that they're all balls. There's a reason why the very first assignment you get in school is bouncing balls. Because these bouncing balls, they'll be everywhere later. To me, animation is what you're seeing right now. When I animate, I always keep track of these points. Doesn't matter if I do a handstand, or I run, or I stop. It's always about bouncing balls for me. And this, actually, is a very good approach. I think as soon as an animator understands and visualizes it, starts to see the animation as these simple shapes, things immediately become easier. If we look again at this jump, it immediately becomes easier to understand how it works, because you're not thinking about this. You're not thinking about a large number of controls. You're thinking only about the points that should move according to certain rules. Once you understand these rules, animation won't be a problem anymore. Let's also look at the broken version. You see there's this freeze that catches the eye. This sudden slowing down, the same thing is here when we fall. You can see how this ball changed its direction. It just went along a different arc for some reason. Let's look at the rotation. Everything is quite simple. If you look at this one, here I did the same thing to make it clearer for you. This is how I work with animation. Well, again, in my mind. Of course, I'm working with characters. But in fact, I perceive them like this. Of course, I work with this kind of view, but in my mind, it's like this. And when you see animation as bouncing balls, it becomes much easier. You have the main ball, it's essentially the center, it's the pelvis, and the legs, the feet. At first, when I worked at Banzai, I learned to work with the layer method. I always started by working on the pelvis and legs. Then, after I worked on that, I moved on to the back, and then to the arms and head. This really helped me to understand animation better. I just started to see it differently. For me, it was always something made up of certain components. There's always the main component, of course, and it should be animated in the best way. So, whenever I started working, I started with the pelvis and legs, and after I did the blocking plus, I moved on to spline, and started working diligently on the pelvis. Once the pelvis looked good to me, once I believed that it could move that way, I proceeded with working on the other parts of the body. So, I think this is one of the key moments in animation, at least to me. Thanks to this, I managed to achieve physicality in animation. So, once you understand it, once you start imagining animation as balls, it will become more of a technical thing, since, of course, there are rules everywhere. Everything moves according to certain rules. And the rest will be about your creativity, what idea to choose, how exactly the character will make certain movements. So, once you figure that out, the rest will be just a matter of technique. Once you got the idea and you know your technical part, you'll just need to create your animation. And the last point for today is arcs. This is the same point as in Disney's 12 Principles. Everything moves according to its arcs, and the same goes for the physical animation. If you look at the current animation, you'll see a lot of arcs here. Everything draws arcs. All legs, all arms draw some kind of arcs, some circles. For me, probably one of the most obvious cases about arcs was in one of my freelance works. Let me show it to you. I made a character with a lot of ribbons. In all these cases, I constantly created circles, as you can see. And the secret to all this beauty is arcs. More precisely, what kind of arcs we draw. Again, imagining the character made up of balls, it immediately becomes easier. It's easier to understand these circles, these arcs. Undoubtedly, in some parts, this is slightly exaggerated for the beauty of the image. And more often, arcs are always refined. If, for example, in your reference, there is an arc that is not very beautiful, not very smooth, then, undoubtedly, in animation, it will be adjusted and improved. One of the examples will be acrobatics and gymnastics. If you look at various gymnastic performances, you'll notice plenty of arcs and a lot of these circles drawn by the different parts of athletes' bodies. So, to sum up everything I told you today, I'll draw a brief conclusion. Today, I mainly considered physical animation, the one closer to realism. In many games, physicality is neglected, or it is exaggerated for greater stylization, and that's fine too. In stylized animation, the contrast is even higher, which makes the animation so attractive to the viewer's eye. In realistic games, there are plenty of cases where animation is being, let's say, pushed as well. For example, if you look at combat animations in many games, you'd see that they're made quite sharp and impactful. But if you'd seen the originals, the mocap, for example, showing the real lifelike motion, you would be surprised at how slow and boring realism is in its true form. But in some games this is presented as a special feature, and that's fine too, since these games are all about hyper-realism. There, the realism is exaggerated and you see that clean mocap that all animators refine for many other games. I believe that understanding of the basics of physical movement is very important, because based on this understanding, you can move into any direction you want. You can choose the animation style like in Sony's Spider-Man cartoon, where they break almost all the rules that I described today. But again, first, you have to understand the laws of physics, so you can break them in a smart way and create believable animations. Of course, not everyone needs to know the laws of physics perfectly. Essentially, everything I talked about today is about the center of mass and other things. No one is talking about Newton's laws, although Newton's laws are actually very necessary in animation. So, I wish you good luck in strengthening your animation basics, as this foundation will help you to achieve a good understanding of movement overall.